Now let's see how the maximal margin hyperplane is found. Letting m sub beta naught beta be given by this, we can reformulate the problem as maximize m sub beta naught beta, where beta naught beta lies in S. Okay, so we're trying to maximize the margin m sub beta naught beta. Here, beta naught comma beta is really beta naught beta 1 through beta p. So I'll just write it like this for short. It turns out that the margin m sub beta naught beta doesn't change if we multiply beta naught and beta by some positive value k. That is, m sub k beta naught k beta is the same as m sub beta naught beta. To see the proof of this, see the optional video or document titled Proof 2. Okay, this fact allows us to impose the following condition. Okay, so the minimum of this, as I ranges from 1 to n, is equal to 1. Okay, so let me write that again. Okay, so this fact allows us to impose this condition here. Okay, to see why, see the optional video or document titled Proof 3. Thus, we can try to find a solution to our maximization problem that satisfies the condition to begin with by imposing the condition here. We now have the optimization problem, maximize m sub beta naught beta, beta naught beta lies in S, given the condition that the minimum of this is 1. Note that m sub beta naught beta equals 1 over the norm of beta times the minimum of this, and that's equal to 1, so we just get 1 over the norm of beta. Okay, so maximizing m sub beta naught beta is the same as minimizing the norm of beta, which is equivalent to minimizing 1/2 the norm of beta squared. So our problem becomes minimize 1/2 the norm of beta squared, where beta naught beta lies in S, given the constraint that the minimum of this is 1. Actually, we can relax the constraint by making it an inequality. So the problem 1, minimize 1/2 the norm of beta squared, given the constraint where the minimum is 1, okay, is equivalent to the problem 2, which is minimize 1/2 the norm of beta squared given the constraint where the minimum is greater than or equal to 1. Okay, so instead of equality, we can replace it with an inequality here. So problems 1 and 2 are equivalent in the sense that the first problem has a solution if and only if the second problem has a solution. Furthermore, the solutions to 1 and 2 will give the same value for m sub beta naught beta. Okay, for the proofs, see the optional videos or documents titled Proofs 4 and 5. We can therefore focus on solving the optimization problem, minimize 1/2 the norm of beta squared, given the constraint where the minimum is greater than or equal to 1. The constraint minimum of this is greater than or equal to 1 is equivalent to the constraint that y sub I times beta 0 plus dot 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 plus beta p xip is greater than or equal to 1 for I ranging from 1 to n. We can reformulate the optimization problem to be minimize 1/2 the norm of beta squared given the constraint where yi times this is greater than or equal to 1 for each of the i's as I ranges from 1 to n. Okay, the requirement that beta naught beta lies in S is unnecessary because the constraint that yi times beta naught plus dot 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 plus beta p xip is greater than or equal to 1 for all of the i's. This implies that yi times beta naught plus dot 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 plus beta p xip is positive. It's greater than 0. Okay, for each of the i's. We can thus reformulate the optimization problem as minimize 1/2 the norm of beta squared, where beta naught beta just lies in R p plus 1. Okay, and the constraint remains this. This is a convex optimization problem where f given by this and gi given by this are differentiable convex functions. Okay, f goes from R p plus 1 to R, and it's defined as 1/2 the norm of beta squared. G sub I goes from R p plus 1 to R, and G sub I is defined as 1 minus y sub I times beta 0 through beta p xip for each I as I ranges from 1 to n. Our convex optimization problem takes the form minimize f of beta 0 through beta p, where beta 0 beta lies in R p plus 1, given the constraint that G sub I of beta 0 through beta p is less than or equal to 0 for I ranging from 1 to n.